So next Friday, we have the week off. So that means we essentially lose a week of lecture. And so my concern is the exam on December 4th. In terms of covering the material, I think if you guys are okay, because exam 4 is on December 4th, and then exam 5 is the week after, okay? Now, I had originally intended to make this a Chapter 39 test. My concern is the amount of time we have to go through the Chapter 34 material.
Professor, we don't see the whiteboard.
Oh, you don't see the whiteboard? I'm sorry. Oh, I had the wrong camera on. Sorry. Oops. Okay, is that better?
Yeah.
Okay, sorry about that. For some reason I thought we were already on. I was showing you the whiteboard. Okay, so I'm thinking that we can make exam 4, chapter 32 and 33 exam, and this one 34 and 39 exam. Does that sound okay? Generally, I only give one problem on this chapter. Okay, so why don't we do that? Okay, so let's make exam 4 on chapters 32 and 33, and exam 5 on 34 and 39. And this is not going to be, it's not going to be as long as this exam anyway, because usually I only put one exam problem on this topic. Okay. Any questions on that or concerns? Okay. So what I want to talk about today is RLCAC circuits, and I want to start on chapter 34 today. So the second half of the lecture will be on chapter 34. The first half I'm going to finish off chapter 33. There is a topic that I'm going to cover called transformers. I'll do that in the lab on Monday. Okay, so I really don't envision finishing up 34 today, and that was my concern regarding exams 4 and 5. If I get far enough, if I actually complete the Poynting vector, I think the rest of the chapter I might skip, because the rest of the chapter is just a bunch of plug and chug problems. Okay. All right. Any questions? Okay. All right. I did want to say something about exam 4 that I might not have mentioned. And really, it had to do with problem 2. Well, it had to do with problems involving force in general. Because you did have problems involving force on exam 3. You did have problems involving force in exam 3. If you have a force problem, what's the first thing you should do with the force problem? Anybody? What's the
repeat that?
I'm sorry?
Sorry, repeat that.
What is the first thing you should think of when you're doing a force problem?
Yeah, probably force body diagram.
Yeah, so a lot of people didn't do that. Okay, a lot of people didn't do that. And I'm making a generalization between both classes. And so you always have to get into a habit. Anytime you see something involving forces, you want to, whether even if it's conceptual in nature or if it's just a problem you need to solve, you want to draw the free body diagram in order for you to be able to solve it. Okay? It's really hard to do it just off the top of your head without a picture. And you're going to, those of you who take statics, or maybe you've had statics already, you probably have been reminded of that many times. When you take 215, you're going to hear that a lot, especially when you do the first part of the course. Not the first part, the part of the course on simple harmonic motion. Okay, so don't forget that the free body diagram is very important. That's one thing that people forgot. Okay. Last time we introduced the concept of phasors that allows us to study circuits. And I want to look at really probably the most important problem in this chapter is a circuit that's driven by an AC power supply and has a resistor, a capacitor, and an inductor in series. So you see in the drawing. And the question is, what is the resulting behavior of your circuit? And again, one can look at V sub R, V sub L, and V sub C as a function of time, but really the most important thing that we look at is the maximum values. And the RMS values are just going to be the maximum values divided by the square root of 2. Okay? So really what I want to do is learn how to figure out big V sub R, big V sub L, big V sub C, and really phi. And we talked about phi, the phase shift, last week. And we saw an example on Monday where I did the R and the L circuit. And I expect you to be able to do the R and C circuit. I just don't have time to do every single combination. So what do I do in this case? Well, let me draw a phasor diagram. Since they're all in series, what must be the same with each element if they're all in series?
Current.
The current's going to be the same. And so let me draw a phasor representing the current. And I'm always going to draw it, I'm always going to start out by drawing it along the horizontal axis, just because it makes the rest of the drawing easy to do. And again, you have to imagine that this thing is rotating at a rate of omega. So let me draw the current vector, or the current phasor, I should say. So this is I sub m. That's the total current. And of course, what we learned is that the voltage and the current are in phase with each other for a resistor. So let me choose red for the voltage across the resistor. And then let's consider the voltage across the inductor. The voltage across the inductor leads the current. So I'll draw it like this. And then we also saw last week that the voltage across the capacitor is behind the current by 90 degrees. So let me draw this in. Okay, so what I'm going to do is I'm going to take V sub L minus V sub C and put it over here. And let me see if I have another color here. Let me know if you can't see this color. Can you see that color okay?
Yeah.
Okay. So that's V sub L minus V sub C. And so the voltage across the resistor plus the voltage across the combination of L and C is going to give you the power supply voltage. And then the phase shift between the power supply voltage and the current is phi. And in this particular drawing, the voltage leads the current because V sub L is bigger than V sub C. If I made V sub C bigger than V sub L, then this thing would be pointing down in this quadrant. Is everyone clear on this? And so if I use the Pythagorean theorem, isn't it true that V sub M is the square root of this squared plus this squared? And of course, all of them depend on current. And so I can write I times V sub R. And then this is going to be, this thing in parentheses is going to be I sub M times X sub L. And then I sub C minus X sub C. And of course, oops, I sub M. I can factor out the I. And that term in the radical is called the impedance. So let's solve for I sub M. And we have the expression for the current. And Z we call the impedance. We can also figure out some other things here. The tangent of phi is V sub L minus V sub C over R, which is the same thing as X sub L minus X sub C. Oops, that's V sub R. This triangle that I have formed is called the impedance triangle. Okay, so let me go to the drawing that I have in the notes. And I've drawn, in the notes, I've drawn the phasor diagram at two different angles. But that first one is, the first one that I draw is the one that helps me get all the information I need. Okay. And the component of Vs, or V sub M, the component of that power supply phasor along the x-axis, really along the I sub M axis, is proportional to the resistance, and the component of V sub S perpendicular to the I sub M axis is proportional to the reactance. If I were to express my power supply voltage in terms of complex exponentials, then the component along the x-axis represents the real part. In other words, I can represent this in the following way. This means real. If you know Euler's expression, the real part of this is cosine omega t. So this is the real part of E sub s times e to the I omega t. The part along this axis, the axis of I sub m, is the part that contains the resistance, the real part. And then the part along this axis is the imaginary part. Okay? And I don't want to get anywhere beyond that. We can also write an expression for cosine of theta, phi I mean, which is going to be adjacent over hypotenuse. Well, let me do it this way. I don't know if you realized, since if I draw my triangle, by the way, that triangle is called the impedance triangle. If I get rid of the eyes, I still have the same thing. Similar triangles, right? That's called the impedance triangle. So I can do the same thing for sine of phi. Questions so far? Because I'm writing down a lot of relationships. Again, the impedance is just involves the resistive part of your circuit, the resistance, and then this is part of the reactance. So this is the total reactance of the circuit. This is the resistance of the circuit. And when you write it this way, then you've written Ohm's law in kind of a generalized way. If you look at it, the units for this thing is ohms. And so the current depends on the value of R, the value of L, the value of C, and the value of omega. And there's our impedance triangle. And you can find out everything you need to know from that triangle. Okay, and again, when I draw this triangle is based on this being, this V sub m is projected along the axis of IM. Okay, not the x-axis, but the axis that forms IM. So the phase angle. Let's talk a little bit about the phase angle. If X sub L is greater than X sub C, meaning the voltage across the inductor is bigger than the voltage across the capacitor, then the current is going to always lag the voltage. And that happens when the frequency is high, because when the frequency is high, this term is huge and this term is small. Because remember, X sub L is omega times L, and X sub C is 1 over omega C. So when omega is big, this term is bigger than this. This term dominates, and so our phase angle here is positive. When V sub c is big, in other words, when X sub c is big, then the current will lead the voltage because this guy will be in the fourth quadrant. And then the other case is when X sub L equals X sub C. When these two voltages are equal to each other, this term disappears. That is a special case. That's called resonance. And in the last lab, you're going to be looking at the resonance of the system. What that means is that you've set the frequency of your power supply at the frequency in which the energy wants to oscillate between these two. Remember, we talked about the LC circuit, and in the LC circuit, the natural frequency of oscillation is determined by 1 over the square root of LC. And I'm going to call that omega naught. That's the natural frequency of oscillation of the system. And when you do that, the sum of these two go to 0. And the voltage across this guy is the power supply voltage. You get maximum energy transferred to the resistor. You get maximum energy transfer from this guy to this guy. Of course, then you're also getting maximum power loss.
So that means, so the resonance means like the inductor and the capacitor basically negating each other?
Yeah.
Or, yeah, okay.
Yeah, they're negating each other at all times.
And so basically it's like there's just a resistor in the circuit.
That's right.
Okay.
All the energy loss is due to this guy, right? Even when you're not a resonance, all the energy loss is due to this guy.
I can see this coming on the test.
I mean, when you take 215, there's the same issues when you talk about you have a mass in a spring and you drive it with a function that varies sinusoidally with time. In other words, imagine my hand is a driver. I have a mass in a spring and I drive it. Okay. I can make the amplitude of oscillation get bigger and bigger and bigger. I mean, I can maximize the amplitude of oscillation by driving it, by moving my hand up and down at the same rate in which the system wants to oscillate at, the natural frequency of oscillation. And then the energy that I'm transferring from my hand to the object gets maximized. And that's called resonance because you're driving the system at the frequency it wants to oscillate at. That make sense?
Yeah.
So I'm going to switch cameras and I'm going to show you an LRC circuit that I've hooked up and we can take a look at the phase relationships. Okay, so I need to connect my other camera. Sound will change. Okay, so there it is. Let me just blow it off. We're going to have a great trace. It's not very stable right now. So let me, I have this set to 5,000 hertz. And there you see the signal. You see the power supply voltage, which is in yellow. And you also see the voltage across the resistor. Now I'm going to change the frequency of the circuit. Actually, let me change the inductance. Let me increase the inductance first. Oops. I have a stable trace. Let me change channel 2. So you can see it better. Okay, I'm going to increase the inductance. I went the wrong way.
So red is VO.
Red is the voltage across the resistor. It's V sub R.
Oh, the resistor. Okay. And yellow is VO?
Yellow is VN, yes. I'm having trouble with the trace.
Oh, okay, I see.
And if you can tell, I'm increasing the phase shift, but my trace is bad. Okay, as I increased, I don't know if you noticed, as I increased the inductance, the phase shift was getting bigger. Let me try it again. Did you notice the phase shift is getting bigger? I'm going to go set it back to what I had it originally. Did you notice the phase shift gets smaller? I reduced the inductance. I'll go back. I'm going to increase it again. You see the relationship the phase shift getting bigger? Now I'm going to decrease the frequency. I'm actually going to set it to about 1600 hertz. And let me set, that voltage is too big. Now notice what happened to the phase shift. It's almost zero. But right there, the phase shift is zero. You guys see that? And now I'm going to decrease the frequency, so now the orange is going to be behind. You see that the orange now is behind because now the capacitor is dominating. Now X sub C is bigger than X sub L because I'm making the omega times L smaller. Do you all see that? Now when you do the LRC lab, you will not have the advantage of using the scope, unfortunately. You're gonna use this scope, just to monitor the power supply voltage. But it would be nice if we can use this because then you can see what happens to the phase shift. You can clearly see what I'm doing here as I do this. The capacitor is starting to dominate more and more because the phase shift becomes more negative. Again, I'll go from that, I'll go to above 1600 so you can see the phase shift go to zero and then go in the other direction. And I'm increasing it slowly. So you see a change, right? Okay. So that's the LRC system. So basically, resistor, capacitor, inductor in series, and that's the last slide you'll be doing. You're going to be analyzing the circuit. You'll be collecting a lot of data for this circuit. Okay. Any questions on this? And the circuit is, I don't know if you can see my finger, it's right here. Okay, I have You can't see the inductor because I have the inductor I'm using is a box where for which I can change the inductance. And now I turned off the inductor. You can see the capacitor dominates. Okay, questions on that circuit? Okay, let me switch back. All right, I just want to make sure you guys can still hear me. I switched microphones. So before I talk about power in an AC circuit, I want to ask you a question involving AC circuits. Suppose I do the following. So it's a conceptual question, so I need your input. I have power supply. I have an inductor. I have a light bulb. Here I have a capacitor. And I have a light bulb. Let's adjust the frequency of the power supply. Let's focus on low frequencies. Let's assume the frequency is low. What should I observe? Remember that x sub L equals omega times L, and x sub C equals 1 over omega C. Well, at low frequencies, this is very large. I mean, think of the current think of the current here and think of the current here. Okay? The current here is going to basically be the power supply voltage divided by this impedance. And over here, you're going to have the power supply voltage divided by this impedance. That's going to be your current. So at low frequencies, what's the current going to be like here? At low frequencies, this thing is going to be huge. No current here, the light bulb will not go on. At low frequencies, this is very small compared to this. So all the voltage, you're going to have current through here, and all the voltage drop will be across the bulb. And so this bulb will go on, this one will be off. So what happens as I increase the frequency? Well, as I increase the frequency, this gets bigger, so it means the voltage drop across this guy will get bigger. This will get dimmer. As I make the frequency bigger up here, then this gets smaller. So now current's starting to go through here. And the bulb will start to get light up. So for very high frequencies, this will essentially be 0. And all the voltage drop will be across this guy. And this will be off. Well, Tyler made a video for us. So let me show you this YouTube video that describes this. Okay, here we go.
So in this demo, we're talking about frequency dependence of circuits. On the left, we have an inductance substitution box set at 9 millihenries and a small light bulb. In parallel, on the right, is a capacitance substitution box and a small light bulb. We have a frequency generator generating a sine wave at approximately 70 Hertz right now. As you can see, all the voltage right here is on the light bulb, and as we go up through the frequencies, the voltage suddenly goes very dim on the light bulb for the inductance and very bright for the light bulb on the capacitance. We can go back down and we can see the transition between the two.
I can forward the links to those videos for you. This one I don't want to show you.
So in
yet.
this demo, on the right, there is a...
Sorry. I will show you this one later. Okay. Questions on that? So let's talk about power in the AC circuit then. If we have a pure inductor and the pure capacitors, they don't lose any energy. Okay, ideal inductor, we're talking about ideal inductor and ideal capacitor. They don't lose any energy. So for an RLC circuit, the power that's dissipated, of course, is I times V. So let's look at power as a function of time. Okay? And then our goal is to calculate the average of this. So let's write an expression for the power, and then let's see where we go from there. It's interesting how much information we can get out of this simple circuit. Okay, so we write P at any time is I times V. And I is just I max cosine omega t minus phi. And I want to look at the total power in my circuit. So then I'm going to multiply this by the voltage across the power supply. Like so. And let me collect the terms. What I want to know is the average power in a cycle. The goal, find P average in a cycle. Whatever omega is. Okay? So that means I have to integrate this. To find the average of a function, I have to integrate it. So let's hold off on that. I'm going to have to do this in a fashion that makes it easier. I don't want to just integrate this straight out. I want to do it the easy way without doing a lot of calculus. I'm going to expand this out. And you know from the trig identity, it's cosine, cosine, sine, sine, right? I hope. If you don't know what it is, then just look it up. What's the plus? And let me write it again. This is cosine squared. So I'm going to take a time average of this term and a time average of this term. Look, we did the time average of cosine squared. What's the time average of cosine squared? From last week. Do you remember what the average of cosine squared, without having me, because I'm not going to do the integral, I'm hoping you remember. What's the average of cosine squared?
So I'm looking through my notes.
Is it 1/2?
It's a half, yeah. So this is a half. So now I need to figure out the average of this thing. Now, think about it. I'm going to be averaging this function. You know how this function is. This is an odd function. If I integrate from 0 to 2 pi, the function is actually symmetric about pi. So in other words, the function will look somewhat like this. Well, it'll be twice, in fact, it'll look more like this. So that's what this function is going to look like in one cycle. So what's the average of that? Positive, positive, negative, negative. You have positive area, negative area, negative area. And their time intervals are the same, so this integral has to be 0. That average has to be 0. And if you don't believe me, go ahead and do the integral yourself. The integral of an odd function over a symmetric interval is always 0. And so what I'm left with is P average is 1/2 I sub m V sub m cosine phi. Cosine phi is called a power factor. Make sure you know what the power factor means. Okay. From our impedance triangle, that we drew earlier, this is the impedance. This is x sub L minus x sub C, and this is R. This is phi. Cosine of phi is R over our total impedance. And I don't want to write it all out explicitly. Okay? So let's write the power factor as R over Z. And let's write V sub m as I sub m times our total impedance. Does these cancel? And what I'm left with is 1/2 I sub m squared R. So you can see all the energy that's dissipated in a cycle is due to the resistor. Make sense? Okay, so let's get to one bit faster here. If I want to, I can write this in terms of RMS current. Remember, I RMS is 1 over the square root of 2 I sub m. If I square this, and if I square both sides, I get I R ms squared equals 1/2 I sub m squared. So this is I squared RMS times R. So the average power, the average energy is dissipated by the resistor. Now, let's look at I and P again. Let's just keep doing our analysis. In fact, I'll say a few more things than what's in the notes. I sub m is equal to V sub m over Z, which is V sub m over the square root of R squared plus X sub L minus X sub C squared. And we can write what X sub L and X sub C are explicitly. Now when X sub L equals X sub C, then Z equals R. And all the voltage of the power supplies across the battery. We get maximum energy loss. Maximum energy transferred is to the resistor. And that's called resonance, like I said before. Let me say a few more things about power. So I want to look at this expression in more detail. I want to look at P average in more detail. Well, I can write this in terms of Z. So what is that going to give me? It's going to give me V sub m squared R. And then in the denominator, I will have 2 times R squared. And let me write out what these terms are. I'm going to write it in a way that's commonly written, especially the lab that we're going to do. Okay, so what I'm going to do here is I'm going to factor out omega squared, sorry. I'm going to factor out omega squared all the way out of here. sorry, not omega squared. I want to factor out 1 over omega squared. And let me put this up in the numerator. The last thing I'm going to do is I'm going to factor out an L squared from here. I'm going to factor out the L squared. Forgot the 2. Sorry. Okay. And we showed that when this is at resonance, this term is at 0. So at resonance, omega is equal to, in other words, these two are 0. Or omega squared is 1 over LC. So that means omega is equal to 1 over the square root of LC. And I'm going to call this omega naught. So I'm going to replace this with omega naught. The frequency then is 1 over 2 pi times 1 over the square root of LC. Now, I can also obtain this by, if I set this equal to 0, that means I want omega L equals to 1 over omega C, and I'll get omega squared equals 1 over LC. So I can get it straight from there when we're at resonance. Because we're in resonance, these two are equal to each other. Does that make sense? And so this is a common way to write the power. And in the lab, the power expression will be written this way. And in fact, we can write this current in a similar fashion. In fact, you can write the current in this manner. The average current. This is a squared. Okay? So these are other ways we can write everything in terms of omega. We can write in terms of the resonance frequency. And you can show that this is maximized when these two are equal to each other. So how do I maximize that function? How do I maximize the function with respect to omega? That'll tell you it's maximized. Okay? And now, if I have time, I will do this calculation in the lab. It's fun. Okay? And then you can do a similar thing for this guy too. You can show that the maximum current occurs at this frequency. Now, I ought to warn you. I don't warn you about this. So, the voltage across at resonance, the voltage across the capacitor, the voltage across the resistor is maximized at this frequency when omega equals omega naught, the natural frequency of oscillation. The voltage across the inductor and the voltage across the capacitor is not maximized at this frequency. Okay, it's only the voltage across the resistor that's maximized at that frequency. Now, granted, if R is small, the voltage across the capacitor will be almost maximized at that frequency. Okay, if R is small. And how do I show what frequency the voltage across the capacitor or inductor is maximized? I write the expression for the voltage across the capacitor or the voltage across the inductor, and I differentiate that function with respect to omega and set it equal to 0. In principle, it's easy to do. It's actually not a hard calculation. Any questions on this? Okay. So let's look at resonance. Like I said, the resonant frequency is 1 over the square root of LC, and we saw this when we talked about the LC circuit in lab. Okay. Now, what if you plot current as a function of omega? Or if you plot, you don't have to plot current as a function of omega. You can always plot current as a function of frequency. In my graph here, I plotted current as a function of omega. And if you make that plot, if you plot the equation for the current that I showed you, it could be the current or the average current. It doesn't matter because the average current is 1/2 the maximum current. So that factor over 1/2 is not going to change the shape of those curves. But what you find is, in this graph here, on the vertical axis I have I and on the horizontal I have omega. What you find here is if you vary R, each one of those graphs I varied R, as R gets smaller, then the graph narrows. The peak is very narrow. Okay, as R gets smaller, the peak gets narrower. And the peak of that graph represents, the peak of that graph occurs at the resonance frequency. So you see in that graph, the magenta graph, the one that's wide, that's 10 ohms. And the orange one is at 3.5 ohms. And notice how much narrower it is. And here I'm plotting, in this graph, I'm plotting current as a function of omega. Okay. Now, I've already gone through this. I went a little bit ahead of myself, but I wanted to do that. Again, the power as a function of omega can be written in this form like I have on the board. And we can plot this graph too. The graph is actually going to pretty much have the same shape, just the width is different. This is the graph, and let me allow you to see a bigger version here. This is power on the vertical axis and omega on the horizontal axis. You can also plot F on the horizontal axis. It really doesn't matter. But again, you see here as the resistance gets smaller, the peak gets narrower. And one thing we look at is called the full width at half maximum. We actually look at the width of the peak at half the maximum. Because it has an important significance, it turns out. So that where you see in the graph delta omega naught, that's how wide the graph is at half the maximum value. And that guy changes as the resistance changes. And to describe the RLC circuit, we also define something called the quality factor, which is evaluated at the resonance frequency. And it turns out that the quality factor is omega naught, which I didn't write in there, but it's omega naught divided by delta omega. The quality factor is omega naught over delta omega. The narrower the peak, the greater the quality factor. So imagine if you're designing a circuit to tune to a radio station, would you want the quality factor to be high or low?
You want it to be really high, right? Because then it'd be near perfect frequency.
You would pick out that frequency for that radio station, because if you make it real low, you're going to pick out a lot of radio stations. And then when you listen to it on the radio, guess what? You're going to just hear all kinds of stuff, right? You'll pick up 2 or 3 radio stations at the same time.
Is that why you pick up like 2 at the same time when you're changing channels, because you're moving the frequency into like 2 areas where you get a slight current?
Yeah, I think in those cases, those frequencies are too close together. I mean, I guess there's a limitation. There's a limiting factor as to how well you can pick out that frequency. How big you can make Q. But you're right. When you pick up two stations, the width of your of that graph is a little bit too wide, and so you pick both of them up. Most likely, you'll pick up one better than the other. So in the lab that you're going to be doing, you're going to be measuring the quality factor. And you can show that the quality factor is omega not L over R. And typical values range between 10 and 100. When you do the, you're not doing that lab next. Those of you taking 215. Normally we do something called the driven damped harmonic oscillator in 215. You're not going to be doing it next semester because it's impossible to do at home. So when you do this lab, you actually measure the quality of the damped harmonic oscillator system, and Q is like 200 for that system. For our lab, we'll be lucky if we get Q of 10. The lab we're doing, the LRC lab. So that quality factor is defined for any system for which you have a driven damped system. Where does that Q come from? Where does this Q come from? Well, it comes from the following. This is the definition of Q. Q is defined as 2 pi times the maximum energy per cycle divided by the energy loss per cycle. That's how you define it. So I can derive that omega naught L over R for our case. It's really not that hard because the maximum energy in a cycle, you can write it as 1/2 L I max squared. But in the denominator, if I want to find the energy lost per cycle, I actually have to integrate the power. Like I got to integrate this over one cycle. And that'll give me the energy lost per cycle. Well, that's actually not that hard to do. I don't have to do a lot of work because
What's that top bound of your integral?
this one, it's it's the period.
Oh, that's t. Okay.
Yeah, which is going to be omega 2 pi over omega. And we're doing this at resonance. So this is evaluated at omega equals omega naught. That's how we define our quality. So P average is 1 over the period times the integral from 0 to t of I squared r dt. Well, we know what P average is. So then this integral is just going to be 1/2 times 1 over t times I sub m squared times r. So I'll put that in the denominator.
Should we multiply the t?
Yes, sorry. Thank you. The I sub m's cancel. The 1/2s cancel. I forgot my 2 pi here. And so I end up getting 2 pi L over the period. What's 2 pi over the period at resonance? Okay? And that's how we get our Q. And one can show, and if I have time in lab, that this is equal to omega naught over delta omega, where delta omega is the full width at half the peak. The width of the graph that you see there at half the peak. Okay? Questions on this? All right. So let's continue. So suppose now, and I've covered everything I needed to cover for AC circuits. Now I want to do some examples. I want to talk about a couple of examples. How many I do is going to depend on how much time I have. But suppose I have, instead of having the parallel case, the series case, I have the resistor, the capacitor, and the inductor in parallel. In other words, let's have this circuit. Now what? How do I solve that problem? Well, I draw my phasor diagram. What do we know? Well, the voltage drops are all the same.
Also, then you can just set them equal to each other, right? Like your equations for voltage across each of the components.
Yeah, I could, but I want to use the phasor diagram to be able to understand this circuit. Because the graphical way is just so much faster. So I want to draw phasor diagram representing the circuit, and you know that the voltage across each one of these guys is going to be the same, right? So I want to represent that. So let me draw V like this. Of course, the current's going to be in phase with the resistor voltage. Right, each one of these are going to have a different current going through it. So, if this is the voltage across each one, then what does the current through the capacitor look like? Or how should I draw the current through the capacitor? Well, the current, go ahead.
Is it behind by like 90 degrees?
Behind which one? Is it behind?
Capacitor.
I mean, doesn't the current lead the voltage in a capacitor?
Oh, that's true, yeah.
So then, and it leads it by 90 degrees. And then what about the inductor?
Wait, would that lag by 90 degrees? Or it would also be with the, oh, that's kind of weird though for this because,
It's different, right?
yeah, it's different than, yeah, that's weird.
And then let me draw I sub L. And then let me draw here I sub C minus I sub L. Not blue, let me use a different color. Purple. And then our total current is this. And then the angle between I and the power supply we'll call phi.
Hey, Professor,
Yeah.
are you okay with another person from a different section joining to do this or to like watch this?
Yeah, that's fine. Is he joining with you or?
Well, yeah, he just asked if he could join because we're doing the RLC circuit.
Yeah, that's fine.
Okay.
Although we will be taking a break in a couple of minutes because it's what, 12:20 almost?
Yeah.
Okay. Let me check my time. I have my watch near me. Okay. Okay, so where are we at now? Okay, so I then is the square root of I sub r squared plus I sub c minus I sub l squared. And so we can write this as V of the power supply, V sub m or V sub s, over R. And then this one's going to be and then you can factor out the V's. So that's I. Okay, but your impedance for the circuit looks different. I mean, your impedance, let me show you the equations. So that's my phasor diagram, and in the picture I've shown shown it at two different angles. But my impedance is I have a mistake in my notes. This is 1 over z. So z is 1 over this.
What does Z stand for again?
The impedance, that's basically
Okay.
this whole thing. Well, not this whole thing, but 1 over this thing. Yeah, there's a mistake in my notes. It should be V over. There's a mistake in one of those equations. Sorry about that. The third line, there's a mistake. So this is Z. And of
Oh,
course,
wait, no, that's
I'm sorry?
it's to the negative 1/2, right? So that would be
Yeah, but if you look at the equation above it, it's not to the negative 1/2. It's to the positive 1/2. And I was trying.
oh, you okay? I see.
Yeah, and I messed that up. I got to correct that. Sometimes after like 2 or 3 times teaching it, I noticed the mistakes. So that's Z, and really what I was trying to do is write it in terms of Z like that. So Z is that stuff to the minus 1/2. Okay. And again, we could draw our impedance triangle. Since V is common to all of those, okay, and this is phi. Since V is common to all of those, then this is going to be and so tangent of phi is going to be equal to 1 over x sub L minus 1 over x sub, 1 over x sub C. One over R. Okay, and I found I'm not going to derive it, but there's even an equation for the quality factor for this circuit. One interesting question for this circuit let's say this is not there. What happens when these two are equal to each other?
It's just the battery's just shorted, right?
There's no current. When these are equal to each other, there's no current. Even though there's current going through each one of these two, because these two are 180 degrees out of phase, if there's no resistor here, there's no current in the circuit. The power supply, there's no current coming from the power supply. The total current is zero.
Oh, because that second term would be 0 and the first term would be undefined. Because R would be 0.
R would be 0, yeah. Isn't that interesting? You have a homework problem on this. And in fact, after lunch, let's eat something real quick. After lunch, maybe I'll show you a video, one of Tyler's video. I had Tyler create another video for that circuit, and it hopefully help you with the homework problem. I am going to also discuss a homework problem. I put a harder homework problem, but I want to discuss it so you can understand how to do it. Okay? So let's take a break and meet in 20 minutes.